as a part is created. And there are some challenges associated with this because it's multi-material, multi-process. There are a lot of hurdles that have to be overcome when we're manufacturing composite parts and structures. It can be difficult to design and model. Process controls, sometimes a challenge. We have ongoing and notorious challenges associated with cycle time and scrap. And this is not to say that these issues aren't being addressed. They are, of course, and being addressed in serious ways. But these are some of the challenges that composite fabricators have always faced in the industry in general. So kind of hand in hand with this is the fact that composites manufacturing is highly engineered and it's what we call non-standardized, which means materials can be customized to meet a variety of applications and mechanical needs. And of course, that's a big strength of composites manufacturing. And it's kind of led to this motto in the industry. I call it the "it depends" motto. What materials and what processes are you going to use to make a certain part? Well, it depends. It depends on the part size and geometry and design space and cost requirements and application and end market and certification and a variety of other things. And so this is kind of the environment that we operate in composites manufacturing in general. And now I want to marry that a little bit with what we see happening in additive manufacturing, composites additive manufacturing. So first of all, composites additive manufacturing, the space is similar to composites manufacturing in general. That is, we have the same types of variation, we just have less of it. I think in composites additive manufacturing, we're primarily using thermoplastic materials, and fibers tend to be either continuous or chopped. We don't have any woven or braided fibers yet in additive manufacturing. And so it's a fairly limited scope, but we still have some of the same variation that we enjoy in composites manufacturing. But the big difference here is the user experience and the user expectation. In additive manufacturing, the user expects to develop a design. They want to pull that design into their additive system in the slideshow software, and then they want to print it. And that's pretty much the really basic steps involved. Of course, it's not that simple, but I think that's the user expectation. The user also assumes the slicer will help them make decisions about fiber placement and fiber orientation and design optimization. And in the supplement, you'll see a story that I wrote about how some of that optimization is taking place right now. But the big difference here is that these additive systems are taking over a lot of that expertise that we normally would expect in composites manufacturing. And that box, that software and that manufacturing system, that additive manufacturing system, are taking over a lot of the computation and optimization that we might normally do manually or with the assistance of software and other systems. And this has really led to what we call democratization of composites, and that it's making composites manufacturing more accessible to people who really don't even know or understand what composite materials are, and in fact maybe making composite parts without even realizing it. And it's created some new terminology, including this one here, composites machine. We're actually hearing that term in the additive manufacturing space, references to a composites machine. And of course, in the composites manufacturing industry, that's an idea that does not really exist right now. So it's really exciting. I think we're seeing a lot of merging of composites manufacturing ideas with additive manufacturing ideas and technology, and creating a lot of opportunity in a really dynamic space to do things, to manufacture composites in new and exciting ways. All right, I'm going to talk about large format composites real quick. Large format composites, it comprises usually a robot-mounted or gantry-mounted extruder that places material, typically a thermoplastic with chopped fiber, typically chopped carbon fiber, onto a horizontal surface, and it builds that up into the shape or a part. That can be applied vertically, as you see here in this mTORUS system, which just came out, which builds up parts vertically on a movable table. But the emphasis here is large parts at relatively high speed. We are seeing some production of large parts with these large format systems, mainly in marine and automotive. But the real sweet spot so far with large format is in tooling. And that sweet spot is in between sort of the high-end Invar steel and aluminum tools and the lower-end tools that might be developed with tooling board. And again, we're talking about high speed. We're looking at high-speed, low-cost tools that can help bring a product to market more quickly or help develop a prototype more robustly and quickly than might be possible with other materials. Of course, Invar steel and aluminum are expensive, can be expensive, and can be time-consuming to produce. The challenge here is CTE, coefficient of thermal expansion. Composite materials, especially a thermoplastic with chalk fiber reinforcement, is going to behave differently from a thermal perspective than the part it's molding, and that can create some challenges. These challenges are not insurmountable. You'll find in the supplement a story about Ascent Aerospace and some of the work they're doing to develop tooling using large format AM and how they overcome some of these CTE challenges. The other limitation is the number of thermal cycles that an additive manufactured tool can be passed through. So again, we've got a sweet spot here between metallic tools and tooling board for tooling applications, and I think there's great opportunity here. All right, so that's it for my summary so far of what we've got. I'm going to hand this off to Hannah. She's going to talk about some of the stories that she developed for the supplement and how she sees additive being deployed for those. So Hannah, it's all yours.
Thanks, Jeff. Okay, so kind of as Jeff's been saying, and Ginger will sort of go into more of next, there are a lot of kind of new developments that we've been seeing in additive technology for composites. And with this, we've kind of been seeing composites additive manufacturing kind of increasingly enabling applications in a variety of end markets, especially for, end use products, as well as prototyping and tooling like Jeff was talking about. So this is in no way an exhaustive list, but just want to show a little of that scope and quickly highlight a few examples from companies we've been talking to lately across marine, wind, construction, and kind of automotive, motorsports markets specifically. So first, a couple of quick examples in marine. So MAMBO, which stands for Motor Additive Manufacturing Boat, the BO in boat, is a demonstrator motorboat project completed by Moi Composites, which is a company in Italy. I know we've covered a couple times before. They developed a continuous fiber 3D printing process called CFM, or continuous fiber manufacturing. It's a deposition-based technology using continuous fiber and UV cure mounted on robotic arms. So one of the things they do is they call it hybrid manufacturing, where they basically 3D print a structural core, like you can see on the left here, made from continuous fiber reinforced polymer, and then use hand layup or some other type of process to kind of laminate another fabric and resin over top of the printed core, combining additive manufacturing and traditional layup processes. So with MAMBO, Moi Composites kind of moved more into the marine space to try to explore and demonstrate how this technology could enable the marine industry to produce the highly complex boat designs fairly quickly without the costs of purchasing tooling. So Moi Composites partnered with Autodesk and Owens Corning and some others in the marine industry. This boat hull was designed and printed in 50 different pieces between two facilities with fiberglass and vinyl ester, and then bonded together. You can kind of see that in the picture in the middle here. And then fiberglass is laminated over top to make and finished to make the final shape of the boat. So they're kind of testing this on the waters this summer and using this as an example of, a very large marine end-use part accomplished through 3D printing. One other quick example in marine is a pretty different example, AUVs, or autonomous underwater vehicles. They're very different than motorboats, but according to Dive Technologies, which is a startup in Massachusetts, who came together a few years ago to kind of rethink the AUV, the story is kind of similar to motorboats, and that there's a large degree of customization that goes into these between different customers. They're not typically making huge volumes of the exact same component. So AUVs usually carry sensors or cameras or other kinds of equipment. They're usually made from metal or thermoformed plastic. And originally, the Dive team began working with Oak Ridge National Labs and Additive Engineering Solutions, or AES, in Ohio to use large format additive and discontinuous fiber for rapid prototyping, these tube-shaped fairings that make up the hull of their AUV. And what they realized in building these prototypes is that the components actually achieved the requirements that they needed for the end-use part. So it eliminated the purchase of a mold, allowed for more design flexibility and customization. So this has become a key part of their business case going forward with these products. So next, jumping into marine. So jumping from marine to wind, the wind industry isn't quite as far along with commercialization maybe of AM, but we've been seeing a lot of research and development projects coming up lately targeting the wind industry with composites additive. For example, shown here at the beginning of this year, the University of Maine and several of its partners announced that they've begun a new project funded by the U.S. Department of Energy to use additive manufacturing to produce a large segmented wind blade molds and joining technology to join them together. You can see a rendering of that here of one of the segments, but basically to put together a 120 meter long mold for infusing a wind blade and print it on the University of Maine's large format printer. And one of the key aspects of this project too was material development, because they're working on a recyclable bio-based thermoplastic reinforced with wood fiber that can be both 3D printed and meet the mechanical requirements for this. So that's what they're working on, both for molds and eventually for wind blade components themselves, which, my next slide here, this is in the supplement as well, but there's several other kind of projects going on aimed at this as well, 3D printing composite wind blade end-use components. For example, Oak Ridge National Labs and the University of Maine are both working with Orbital Composites, who Jeff mentioned a little bit ago, on a DOE-sponsored project using Orbital's containerized 3D printing robots that they've developed for on-site printing of wind blade components, which would eliminate, transporting of these large components, increasing production speeds for them as well. Another recently begun project was 3 different GE business units working together with some partners on a 25-month project for 3D printing thermoplastic composite wind blade tips to kind of using thermoplastics to work toward more recyclable materials, as well as decreasing weight and reducing manufacturing costs. So we'll see where this landscape takes us the next few years as they work on these. So in automotive or motorsports, one limiting factor for use of additive in automotive as a whole, I guess, is that automotive components are usually pretty high volumes than what makes sense for AM. But I just wanted to highlight a couple of recent projects, specifically in motorsports, that make use of additive to produce, the highly customized toolless complex parts. One example here is Champion Motorsport, which is a racing company who recently teamed up with Stratasys, which is a 3D printing company, on aerodynamic components for the modified Porsche race car you see here, which competed in this year's Pikes Peak Hill Climb in Colorado a few weeks ago. So Stratasys printed for this more than a dozen parts on the vehicle using 3 different technologies. Some were carbon fiber filled nylon, some were unreinforced nylon, or one kind of newer technology they were testing out with this was a 3D printed Ultim core overwrapped with carbon fiber prepreg, which they used for both prototype parts and a few production parts on the vehicle. The largest part was a 7-foot by 5-foot rear diffuser, which is kind of the black tray looking part that comes off the back of the vehicle in the picture. They used sort of their overwrapped core technology to do a very quick prototype that was tested for this vehicle. were able to do it without tooling and in much quicker time than what they'd been doing before. So we're hoping to, transfer that technology to other applications as well in automotive. One other quick example was Burchella. So it's a fabricator in Italy. They work with motorsports and also aerospace components in others areas. So over the past 4 years, Burchella worked with CMS, which is an Italian multi-axis machining specialist, to prove out in kind of industry cases for CMS Creator, which is a new hybrid machining center that CMS Creator released earlier this summer, combining 3D printing with milling and other machining operations, specifically discontinuous fiber extrusion. So the first use of the machine center has been with Burchella. It's called the Restomod Maserati program that they're part of, and announced earlier this summer, restoring Maserati vehicles with new body components. So this is an ongoing project that they're working on. You can see sort of part of the progress here in these pictures, and one of the molds in the bottom picture as well. Burchella is building carbon fiber pre-preg parts for the vehicle and using CMS Creator, large format additive / milling machine to produce carbon fiber filled molds to produce these parts. So they're seeing a lot of kind of end use cases, both in tooling and end use parts for these. One kind of last end market area I wanted to touch on briefly is use of AM in construction, specifically home construction. So Mighty Buildings is a California-based company, launched last summer, first with its Mighty Mods modular home concept, which are one-story units made with a combination of 3D printed thermoset panels and steel frames built on kind of a large format extrusion-based 3D printing system that Mighty Buildings developed. The Mighty Mods are prefabricated, transported, installed on site. So they've had success with these, and the next iteration is what we kind of talk about in the supplement this year, because it's a product called the Mighty Kit system, which are larger multi-story structures that can be transported farther and come as kits of materials quickly assembled on site. And these are all kind of enabled by a new continuous glass fiber reinforced material that the company's developed, which is currently undergoing testing and moving towards certification. So on this slide, you can see kind of a rendering and a demonstrator unit for one of their new models that they hope to start building for customers by the end of the year. Last slide here, this doesn't fit quite as neatly into my end market theme here, but still wanted to include Caracal AM, which is an Italian company we wrote about in the supplement, which developed a fairly new company that developed a large-scale additive system that's extrusion-based, using a range of resins and discontinuous fibers. That they're, key to their technology is large scale. So they're using robotics and software to print up to 4 meters with the machine, and larger with kind of addition of special rails and things. Focusing on prototype parts and aerospace tooling. So kind of seeing a number of developments that they're working on too, with iterating to a version with continuous fiber and higher performance materials going forward. So I think that's all I have. With that, hand it over to Ginger.
Thanks, Hannah. So I'm going to start with an article that I wrote with DLR, that's the German Aerospace Center, and this was their Institute of Composite Structures and Adaptive Systems in Braunschweig. And the project is called Endless Effect. So they're looking at how to reduce the cost of continuous fiber 3D printing materials. And you can see on the right-hand side, that system starts with fiber spreading. So in this case, they were working with 12 to 24K carbon fiber tow. However, their goal is to go all the way up to 50K. They then spread it, heat it, put it through the melt injection bath, and then hang an L there and go into an ultrasonic chamber. And there you have 19.5 thousand vibrations per second. You have a ultrasonic sonotrode that pushes the fiberglass into the fiber and to improve impregnation. In the middle at the bottom, you can see the different samples. So they were able to achieve 50% fiber volume with carbon fiber PLA, polyamide, and PEI at the bottom, polyether imide. They have started moving up in line speed, and the goal is to further miniaturize this and actually be able to integrate it into a print head. They would still have the standalone system, but it's just to give the industry more options for getting the cost down on these materials, which they feel has been kind of an obstacle to wider adoption. Now, DLR there in Braunschweig is doing a lot of different things in additive. And this slide, I think, is really interesting. You can see in the lower left-hand corner where the endless fibers come in and trying to get those costs down, but then you can see some of their other areas of work. And to me, the bottom is really interesting because you're combining, say, 3D printing with AFP. They're looking at printed pressure actuated cells. So we've been looking at morphing aerodynamic surfaces and surfaces that can respond to pressure. Also sensors being printed into structures. And then on the far right is their additive extrusion innovation lab. And at the bottom, you'll see a link for those articles. I've written several on those, and that's a members oriented association organization that is working towards standardization and more widespread adoption. And I think they're doing a lot of really good work there. So the second article is with CEAD in the Netherlands, and basically how they're responding to their customers' requests as they industrialize 3D printing. One of the first things that CEAD I wrote about is that they've partnered with Belotti, who is a well-known manufacturer of CNC systems, and that's so that they can have this system in the middle called the BEAD, and that's where they will be doing additive manufacturing and then subtractive manufacturing. And a lot of our sponsors today are involved in that same field, right? So then some of the other things they've been doing is adding rotary tables and larger print beds so that their customers can print all different kinds of structures. But most of the article I wrote about actually their migration to Siemens NX. When we write about these 3D printing cells and these additive manufacturing techniques, a lot of times we'll discuss whether it's open materials, open software, or closed materials, closed software. And there are pros and cons to both approaches. I wanted to know why they were moving to Siemens NX. And what they explained was that as they're building all of these cells, if you look across the bottom, they're very customized. Every cell is different. By going into Siemens NX, they've been able to model every different cell, all the different pieces of equipment. So on the far left, you have a dryer where they dry the pellets before they melt and extrude those. You might have different kinds of tooling. And so they can model every bit of it, and they can model its dynamic. So they can model as the tool gets switched from printing to milling, and as the material is being laid and what that looks like. Another advantage is that within Siemens NX, there is a CAD module. So what happens is if you design parts and then you change those parts, when you go to redo the simulation, those operations are regenerated, and that's quite helpful. Also, all of the CEAD machines use the Siemens controller, the Run My Robot controller, so they can improve their accuracy as they go to simulate these processes and these parts. One important thing about, I think, what CEAD is doing is, and I wrote about this, is that they are already involved in the use of 3D printing for serial production tooling. So they have been working with GKN Munich. And the part you see there was split and the machine down, and it provided several intensifiers that are actually used right now in the serial production of the landing flaps for the Airbus A350 and the A330. Now, GKN Munich is going to continue that work with CEAD. They have another project, a 2-year project, along with Airbus, and they will be printing larger tools that use both chopped and continuous fiber. This is stage 2 of a 4-stage roadmap that GKN Munich discussed last year in the symposium that TU Munich held in September. And basically stage 4 is where they move toward not just serial production of tooling, but serial production of 3D printed composite flying parts. The next article was written with APS Tech Solutions. They are a manufacturer of parts for water jet cutters in Austria. They were looking for a 3D printer to help them put 3D printed parts in their systems they're delivering to customers, their modules. And they just couldn't find what they wanted. So they developed their own. It's called the Wizard 480 Plus. It uses continuous carbon and glass fiber. You can see examples on the right. It also can print with copper wire and then off-the-shelf filaments, but they wanted also to be able to print with metals and ceramics, and you can see an example of that in the middle. Those, of course, would be green parts that would be later sintered. Because of the environment they're in, this precision parts for machine tools, they are quite used to a CNC setup, and so they wanted to have a tool exchange. And that would allow them to use multiple materials in a single print. And so that's something that they've incorporated into the machine. In the lower left, you can see an example of some spare parts that were printed for their first customer who bought a machine, which is Stepper. Stepper is a well-known manufacturer of stamping tools in stamping machines in Germany. And that was a camera module on the left, which is multi-material, chopped and continuous fiber. And then in the middle, that's something that Stipper actually did themselves. That's a camera module for a stamping tool, and that has a lot of different 3D printed parts in it. Now, this is what I grabbed today off LinkedIn because I thought it's just another example of why we're seeing more and more multi-material prints. This is something that the DLR Institute of Structures and Design in Stuttgart is doing. They do a lot of work with the space industry. And so this is a piece of a satellite structure. What you're looking at on the left is a base carbon plate that they then 3D printed this honeycomb onto. When they, on the videos, which I have a link to, they actually put it into a vibration tester later, and they'll have a top carbon plate on it. But what they did is, you can see they're doing multifunctional cores with carbon fiber filled peak, and then they move to a tungsten filled peak as they start to print other structures and radiation shielding. So this is just the very beginning of precision multi-material parts we're going to see. Another resource for those kind of developments would be our sister magazine, Additive Manufacturing. And that would be additivemanufacturing.media. They talk about this kind of disruption across materials. So that would be composites, plastics, and metals. Another article I did was with the Chair for Carbon Composites, LCC, at TU Munich. Now, we had worked together last year, Alex Machinsky and I and this group, on a landscape for 3D printed composites using continuous fiber. And this year we kind of went beyond that a little bit and added on what we see happening, which is you have all of these extrusion related AM processes on the left with continuous fiber, and then you have kind of our more conventional processes on the far right, albeit highly automated, and then we're seeing a merging in the middle. And we gave examples of 19 Labs and Aris Composites, and you can see that what they're doing is using the 3D deposition, the 3D printing kind of technology to make preforms, and then they go to a second step, which is a molding step. And what does that buy us? It gives us totally new ways to create higher volumes, compete with materials like SMC, but with continuous fiber, and also add functionality. And then that article also goes on to really give more detail about where LCC is blurring those lines. So in the upper right-hand corner, what you see is a 3D printed interior of a cylinder or drive shaft, and then they're wrapping. They're doing laser-assisted tape winding on the outside. So that would be an in situ consolidation thermoplastic composite technique. And as you see on this cross-section of this drive shaft, they've not only printed the end fitting with the material, the fastener inserts, but as you look down the cylinder, you can see this kind of spiral. Well, those are longerons. Those are longitudinal stiffeners that actually spiral as you go to the other end. So we have this whole new way to think about how we design structures and how we can achieve those. In the article, we discuss kind of how LCC is defining additive composites manufacturing. And it's interesting because they're saying, look, we had these long process chains in composites, and we're consolidating those down to a single point. Instead of having global consolidation of the laminate in an autoclave or an oven, we're doing local recurring heating, not dissimilar to AFP, by the way, and we're eliminating the tool. And then an example where they're also pushing boundaries, Jeff had said most of what we're seeing is thermoplastic, and that's true. However, we do have systems like continuous composites that can print with UV cure resins. Moy in Italy can as well. But this time, LCC went away from that. And what they did is they took the typical extrusion and in the very long, process chain at this figure in the bottom for thermosets, and they compressed it down to where they're using continuous fiber, but they're using quick cure epoxies for automotive. And then they use an ultrasonic technique that they had developed for RTM, where they mix the resin, and then as they're depositing, it's a very quick cure. And this gives us a new way to do thermoset composites. The last article that I'm going to talk about is work that I saw at the MIT Mediated Matter Lab. And this was really interesting because it comes from a totally different place. It comes from sustainability. So how could we make biocomposite structures that are very highly engineered, and we make them with digital techniques, but they're helpful as we move into this new world where resources are stretched and we need to be able to recycle things. So what they looked at was using really abundant biological materials like chitin and pectin out of apples. Chitin is the protein incrustation shells, and cellulose fiber. And they took a KUKA robotic arm, they put a deposition end effector on it, and you can see these 6 barrels that they have. And the different colors in those barrels are different density solutions, right? So at the very bottom, you'll see that scale from 1% to 12% of chitin mixed with acetic acid and water, and it gives these gels. And they print these gels in patterns. So their digital engineering is fairly exquisite, because what they do is they look at, if you kind of go a little bit left of that spectrum of color, you can see the nozzle shapes, the beads. And they can affect the width by the pressure and the speed. They can build multiple layers to build the height of the bead. And then they mess with the what density they want to use. So if you want, a structural vein, you do a higher density solution. If you want to print your thin film on top of it so that you have this wing-like structure, you do that with a lower density, say 3%. Oh, and by the way, when you print on top, the self-bonding, these materials are self-bonding when they print. Another thing they did is, because these are composites and they're based on their aqueous solutions, they actually evaporate, and they have directional evaporation stresses. So that was also designed in so that you could have some of these structures actually curve. So in the middle, right below the dragonfly wing, you can see there's kind of a cylinder. So they can be programmed to take shape as well. And then this is kind of their demonstrator, Agua Hoja. So agua for water, Hoja is like a shell structure. And this was a 5-meter tall pavilion they did that stands at MIT. They 3D printed 95 different parts, and the white spine that holds it together is a plastic. But the rest of it is just this exquisite design of different combinations of biocomposites that can change in their stiffness, their flexibility, or vary rather, and then they can respond to things like humidity, heat, and light. And that is a thing in architecture now. We want structures that can help us as we move into hotter temperatures and how to condition buildings without a lot of energy. And then all of these can be programmed to biodegrade in water. At the bottom, you see some examples of packaging that they made with this kind of technology. These are, biodegradable and sustainable. And that is the end of my presentation.
Okay, great. Thank you, Ginger, and thank you, Hannah. All right, so we're at the 35-minute mark. We do have time now for Q&A. So attendees, if you have a question, you can post it here under the Q&A tab in the webinar interface. Also, we've had some questions about whether or not this presentation will be available. It is available already. If you click on the Handouts tab right next to the Q&A tab, you'll be able to access this presentation there, and you can download it right now. So, Ginger and Hannah, let's go ahead and get to some of the questions. I'm going to answer the first one. I had a couple of questions about how a smooth surface is created for printing tools, and this was related to the photo of the Ascent tool. So I'm gonna go back to that real quick, so that we can talk about that real quick. So the question was about this photo of the Ascent tool right here. How do you get that smooth surface, and also how do you prevent fibers from showing through? So first of all, the fiber loading percentage is typically relatively low compared to traditional composites. So percentage wise, it's probably ranging between 25 and 35%. And then second, when the part is first printed, like if you look at this M Taurus photo here in the middle, you can see that there's kind of as the layers are built up, there's kind of a rippling effect on the side of the part that has to be machined out. So there's a secondary process for all of these for tooling where you have to machine the surface to create a smooth surface. And and some of the systems, including Thermwoods, I think Ingersoll does this, I know that M Taurus does it, offer machining built into the system. So with a large format system, you can print on one side and then move the part over to the other side of the machine and then do the machining there to create the smooth surface. So there is some sacrificial material there that has to be accommodated for during the printing process, and that's part of the design process for these tools. Also, I had a question about CTE and whether the CTE for carbon fiber was larger than that for aluminum. I have to find that out. I think the short answer is yes, but maybe more importantly, the real challenge is predictability. So aluminum is isotropic; it's got the same properties in all direction, and its CTE is predictable. And so in that way, it's probably easier to design for. The CTE of carbon fiber depends on a lot of things, the type of fiber, the type of resin, the fiber loading, and other factors, which make predicting the CTE much more challenging. And so I think that's one issue that has to be considered.
Jeff, there's one thing I'd like to add is that one of the reasons why Airbus and CEAD and GKN Munich are looking at adding continuous fiber into the tools is to control CTE and make it align better with the tooling that they want to produce for autoclave parts.
Yeah, we actually did a story also, which we didn't reference here. We did a story a few months ago on the technology that uses additive to build the core of the tool and then wraps it with continuous fiber to sort of give it that dimensional stability that you would need in a tooling application. Ginger, there's a question here about 3D printing with CMCs or ceramics. I'm not familiar with that. Have you heard of anything about that?
Yeah. So at the high temperature material conference 2 years ago, there were quite a few papers. I wouldn't say quite a few. There were a handful of papers on 3D printed CMCs, and I've been watching it, and I am seeing more and more come about. I know Additive Manufacturing, our sister magazine, they did an article on metal matrix composites, and I know you talked to Greg Mark about that in your podcast on Mark Forged, and he talked about metal matrix composites. I do think we're going to see a lot more of both. I think we're going to see a lot more of 3D printed ceramics, CMCs, and 3D printed MMCs, but we're still at the very beginning of that development.
Yeah, there's a question here too about natural fibers. There is certainly no reason why natural fibers could not be used in additive, and I know that's an option for several systems.
The only issue I would say is it shouldn't. I mean, there's always this issue around the water, but I mean, right now when they are using nylon, they're drying the pellets before they put it in there. So I mean, I think there's a way to deal with that.
Yeah. All right, Ginger, what range of tow can be ultrasonically infused with a PLA or other, and has any work been done or might be planned for PEEK or other high-strength thermoplastics?
So like I said, right now, the first tests were done on 12K and 24K. However, their goal is to go all the way up to 50K input tow and spread that. As far as what they're doing with PEEK, I don't know. I do know that because DLR works across the space and aircraft segments as well as other segments, I know that that's in their wheelhouse to look at. I just don't know what they're going to do. So I can ask that question and see if they're going to do PEEK and PEC and PEK as well.
All right, there's a question here about carbon nanotubes or carbon nanostructures or fullerenes inside powders for additive manufacturing. I've not seen any, the question here is, are there any significant cases in the strength or fatigue results of the parts? I've not seen that. There's certainly no reason why you couldn't functionalize carbon nanotubes within a resin matrix the same way you would in a traditional composites manufacturing process. But I've not seen significant data on that yet. And Hannah or Ginger, I don't know if you've seen anything.
I haven't yet. How about you, Hannah?
The only thing I can think is having seen just, announcements and that sort of thing from XG Sciences and maybe some others from of working toward developing filaments with graphene or nanoplatelets in them, but haven't seen too much on that yet.
Yeah, and XG Sciences is a graphene supplier, and they might have more information about work they're doing there.
Right. Yeah.
And then Hannah or Ginger, I'm interested in learning how to analyze and quality check additive manufactured parts. We haven't dabbled in that too much or haven't seen too much on it. I would say that there's a lot of NDT technology available for composites quality assessment. I would assume the same technologies could be deployed in additive manufacturing, but if either of you has comments on this, feel free.
The one thing that I have written about is Nebumind, Nebumind. That I wrote about them in the 4.0 series last year, and they are working on digital twins that pull process data as you're printing. So that would be heat and pressure data and other data. And so that might be a good place to start. The co-founders are, it's a startup, Nebumine is, but the co-founders worked for In-Factory Solutions, where they developed sensors for AFP and infusion. They also are Airbus. So I would encourage you to reach out to them. That's the one I can think of right off the top of my head.
This is an interesting question from John. Do you think more work is required to develop standards related to these technologies? Are the technologies mature enough to allow these standards to be created yet? Presumably, these are going to become necessary for widespread use of the technologies, especially for end-use part applications. There is a Wild West aspect to additive right now, and it is highly dynamic and susceptible to change, just like the composites industry is. And so there, as Ginger showed in that landscape slide,
Yeah. Jeff? I think we lost Jeff for a second. Okay, so I'm going to pick up. One of the things about standards, and that's where I think Empower AX is so interesting, is Germany is very intent on developing standards, and they are working with VDI and other groups. And so that's a key part of what Empower AX is doing. It is working with the industry and the suppliers, both equipment and material suppliers, to develop standards, and standards that make sense and standards that can help. Go ahead, Jeff.
There's a Wild West aspect to this. As Ginger showed with this landscape, there's a lot of different ways of deploying fibers within an additive environment. But it's also worth noting as well that Boeing is in the process and has already qualified several materials for use in additive manufacturing. So there is, at least in the aerospace side, there is an effort to qualify and certify materials for use in flying aircraft. So I expect we'll see more of that. But the question was, are these technologies mature enough to allow these standards to be created? Yes. Yes, I think that is happening, but there is still a lot of work to be done. And obviously there's still a lot of technology to be evolved and to come out.
I think one important note to make is it's interesting that I would say the most mature continuous fiber printer is Mark Forged. They came out in 2014. They were kind of the first. And they, Grace Nels just picked up and published a news item. Well, I don't know if it's out yet, but we have it in process, where they're going to be part of NCAMP. So they are doing a qualification, a material pre-qualification.
Question here, do we have biocomposites approved on spacecraft and aircraft now? I don't think so. I would be surprised if we did. Ginger or Hannah, any thoughts on that?
Biocomposites, no.
Yeah.
Other composites, yes.
Question here, lots of tooling, marine, civil, automotive examples. What's potential for aerospace structural components? Is it dependent on resin and continuous carbon fibers being used rather than chopped? I think you probably, use of continuous fibers. I don't know of any additively manufactured composite parts that have been certified for flight on a commercial aircraft. I know, like I noted with the Ascent Aerospace example, that the tooling can be used to make aerospace parts. But as far as I know, there are no flying parts yet. And we might check with our friends at Additive Manufacturing Magazine, but Ginger or Hannah, if you have comments on that.
Yeah, like I said, GKN Munich has this roadmap to get to that. And, in one of the articles I wrote on flaperons and exoskeletons, it was part of what TU Munich, is doing. It was after their symposium. And that was one of the things they said, that even though that's definitely on their radar as well, that right now what they're doing is getting a lot of product and process prove out through doing the tooling. And then that's the next step, is to move into more flying parts.
Okay, here's one for either you, Hannah, or Ginger. When we say the word continuous in this context, how long are the fibers?
Well, they're as long as the fiber path is in the part. You know, they're as long as, I mean, I suppose I'm trying to think of the different parts I've seen and how they're printing. You know, you're printing layer by layer. But yeah, it's no different really than the way we would consider a continuous or an endless fiber in a non-additive part, or I would say a more conventional part.
Yeah, I would say if you have a part of, you know, that's 1 meter wide by 1 meter long, and you want continuous fiber to run the length and width of that part, then that is possible.
The difference when you get into this type of manufacturing is that you are not restricted, right? You're not restricted to AFP across the layer. You lay the fiber length in as you need to lay the fiber length in. You lay the fiber path as you need to lay the fiber path, depending on what you're trying to achieve for the load and the other functions of the part. And that's the key.
All right, so a question here about large format. What are the biggest benefits compared to, say, other methods of tool manufacturing? Is it cost or overall time for manufacture? I'd say both. Cost is substantially less, and the ability to make a tool, say, within 2 or 3 weeks versus 2 or 3 months, it's a game changer. And so I think if you look at the story I did on Ascent Aerospace and what they're doing, you'll see the arguments there and for why Ascent has developed this technology the way they have. All right, next question. Are you aware of any chopped conductive staple fibers besides carbon fiber like PET, nylon, Kevlar, et cetera, being used in additive manufacturing for composites? Is that something you can address, Ginger?
Chopped conductive or just chopped synthetic fiber?
It says chopped conductive staple fibers. So I'm wondering if there's Jimmy, if we might need you to resubmit that question, if you can clarify.
You know, I can't remember if I thought, I know I've seen steel, but I don't know in what format. I can't remember if it was connected with additive manufacturing. That's the only other one I could think of that's conductive, to be honest with you. Okay.
Here's a question we get a lot. Beyond the applications you've shown, especially in tooling, do you see this becoming a significant market? Ginger and Hannah, what do you think?
Wait, say the question again.
Beyond applications we've shown, especially in tooling, do you see this becoming a significant end market?
I don't know. Hannah, what do you think?
I mean, just in general, I guess. I don't know. I mean, the folks I talked to, it was like very specific. I mean, I think it, has a lot of use cases and very specific things. The kind of examples I was talking about were more like lower volume or one-off custom type end markets and that sort of thing. So I feel like that's an area I'm seeing where they're, being a larger area beyond tooling.
I think that you're going to see a lot more in machines, robots, the parts like for stepper. You're going to see more and more of that. We're starting to see shoes, carbon in shoes, other consumer goods. I think we're starting to see, a lot of movement. I know 9T has a partnership with a high-end fastener manufacturer, I think in France. I think there are business cases to be made where and the other thing that plays into the hands of additive manufacturing is the fact that we're moving toward an increasingly customized product market, and that could be your car, that could be the things you wear, that could be the machines you want to use. I mean, I think that's a trend that additive will be able to take advantage of.
Yeah, and I would go back to what I said in my introduction, that there's a level of democratization at work here that allows manufacturers or makers who are outside of the composites industry to create composite parts and structures in a way that was not possible, say, 10 or 15 years ago, or even 5 years ago. And that I think that's going to really accelerate what we can do with additive and how we do it. And it's going to, like Ginger noted, it's going to cross over more into other processes. We're already seeing that with AFP. I think we'll see it in other areas as well. So I just think there's a tremendous opportunity here, and there are business cases to be made. Question here about interlaminar adhesion properties compared to ATP and AFP, which use compaction rollers. Yeah, interlaminar adhesion has been an issue for sure. Because you are laying a molten thermoplastic on top of a semi-molten or partially cooled thermoplastic, you're going to naturally have interlaminar, or what we call Z-direction, integrity issues. Different manufacturers or different machinery manufacturers are dealing with this in different ways. Some are kind of using a ultrasonic or vibration technique to try to promote interlaminar adhesion, but I think that's a fundamental weakness. It can't compare to a fully compacted or fully consolidated composite part. So yes, that is definitely an issue. I don't know, Hannah and Ginger, if you want to comment on that.
Well, I think that's why you've seen some companies like 9T do a post molding, and they get compaction that way. Some of the other manufacturers apply pressure as they lay. I think we're starting. I mean, they know it, they understand it, and they're looking at it. And then they deal with it a lot in design as well. The parts are designed in a way where they take that into account. But yeah, you're right. You're always if you're placing in layers, then you're always going to have a problem between those layers more so than, but normal composites do as well. we're also in layers.
Yeah, as Ginger said, 9T Labs actually has, their system consists of two machines. One is a printer and the other is a consolidator to consolidate the part. Aris Composites, which Ginger referenced, is somewhat similar. They lay down preforms that are then transferred to a tool that's compression molded. So that challenge is being met in a variety of different ways. Ginger, there's a question here about the MIT biomimicry technology, the printing with chitin at different concentrations to obtain tailored mechanical properties. Is there any approach for 4D printing, including effective temperature or vibrations to change physical properties? I don't know if that's something you got into with them or not.
I don't know if Laia has done that work. After Laia left MIT, she went on to Tufts at the Silk Lab, and now she's doing architecture at UPenn. But it might be something that Neri Oxman, who headed this whole project and is really well known, it might be something that she's looking into. I have, we've never written about 4D yet. I've always wanted to, just one of those things we haven't gotten to. I do understand what you're saying. I know there are other stimuli you can take advantage of, not just evaporation stresses. And I think that would be something Neri would be really interested in doing. Yeah. But I haven't seen that work done yet.
Okay. Question here for AM processes that use chopped carbon fiber or glass fiber. What are the preferred fiber diameters? Are there special fiber surface treatment requirements versus traditional manufacturing techniques? I don't know about fiber diameters. I don't think there's anything out of the ordinary about fiber diameters involved. In terms of sizing or surface treatment, typically you do not treat or size fibers for use with thermoplastics materials, although there is some research exploring sizings for thermoplastics that might change that. If you are additively manufacturing thermoset materials, that might be a different situation. That's not something we've explored yet, but a company like Continuous Composites would certainly be able to speak to that a little bit more. They're the ones who use thermosets.
Well, and the two things I know about is when a few years ago at CAMX, Owens Corning had a fiber that they were producing and said they had modified specifically for 3D printing. I don't know what's happened to that fiber. I don't know if they've sold it off. The other point would definitely be Continuous Composites, because they've been working with Arkema and Sartomer, Arkema's the subsidiary, to develop materials for their 3D printing process. So I would imagine those micromechanics are something that they're well versed in and able to do.
Question here about slicing software. What slicing and CAM software is at the forefront? What innovative slicer features are being most often requested? I'm not sure I can characterize which slicing software is at the forefront. I do know that one thing we wrote about, or I wrote about in the supplement, is about Teton Composites, which is trying to build these modules that would operate within a slicing software to help the user make more intelligent decisions about the deployment of fibers, whether continuous or chopped, to meet specific mechanical requirements. And the suggestion at the end of that story was that at some point soon, meaning probably in the next 5 years, maybe ideally, maybe hopefully, we would have a unified design system so that we have design and modeling and optimization and a variety of tools all integrated within one system, so that we don't have all these bolt-on and add-on systems that you might need to help to optimize a design. It remains to be seen if that's where we're headed, but we could probably do some research on. It might be worth a story looking at some of the slicing software and how it does what it does and how it accommodates or adjusts for fiber use.
I know one of the articles we wrote on Arrivo, they were talking about slicing software and what they were doing to try to improve the software. In one of the articles I wrote, CEAD was using Rhino 3D's plugin Grasshopper to do slicing, and then APS Tech Solutions is using Simplify 3D Plus out of Cincinnati. So those are some of the ones I've seen. And then a lot of people have their own that are built in-house.
All right, well, Ginger and Hannah, we're at the top of the hour, and we still have quite a few questions here. So what we're going to do is we're going to aggregate all the questions. We'll answer them as best we can, and then we'll distribute those answers to the entire audience that registered for this webinar. Again, if you want to download the webinar, you can. Under the Handouts tab right here, you can download the webinar we just presented. And our contact information is here. If anybody wants to reach out to us, if you have an idea, we'd like to hear it. If you have a question, we'd like to hear it. We're always eager to interact and communicate with folks in the industry. So Hannah and Ginger, thanks again for this presentation. Thanks for your hard work on the supplement. I appreciate it and appreciate you presenting today.
And thanks to all of our attendees. We appreciate it.
Yeah, thanks everybody.
All right, that brings us to the end of this presentation. We hope to see you again soon on another Composites World webinar. You can go to Composites World